Last time we finished up our unit on systems of linear equations by discussing an application to polynomial interpolation, which was pretty cool. This time we're going to be starting a new unit in our matrix series, and this is going to be on matrix operations. And at this point in the series, it's going to start picking up in pace, so buckle up. First, a word on notation for matrices. So we usually denote a matrix with a capital letter like uppercase A, uppercase B, or uppercase M maybe. You don't have to, but you will see this often. Another thing is you may see a matrix denoted by a generic element from the ith row, jth column, right, in square brackets. So we might write that sometimes when it's convenient to talk about what's going on element by element in a matrix. And of course the other way that you're most familiar with is as a rectangular array of numbers. And you could also do this in parentheses. It doesn't matter as long as you are neat with your rows and columns. You will see me do both. And of course these entries can be integers, they can be real numbers, they can be complex numbers, they can even be quaternions, although you'll have trouble doing determinants with that. And when are two matrices equal? They're equal when they're equal element by element, when in each position in the array, notably they have the same size, and in each position they have the same elements. So A is equal to B if and only if A sub ij is equal to B sub ij for all I and for all j. Right, and of course these are bounded by I ranges between 1 and m, let's say, and j ranges between 1 and n, typically. We can talk about m by n matrices, although square matrices are going to start taking a front seat pretty soon. First matrix operation we're going to learn about, addition of matrices. So if you have two matrices A and B, then their sum is defined as this, right? So if A is equal to A sub ij and B is represented by this generic element, then their sum is represented by the generic sums of their individual elements, right? So element by element, we add them together. As examples of this, let's do 1, 1, 1, 1 plus 1, 2, 3, 4. So we add the 1 in this position to the 1 in that position in this, right? These are both 2 by 2 matrices, so we can do addition. And we'll get a 2 in that position. Then 1 plus 2 is going to be 3. 1 plus 3 is going to be 4. 1 plus 4 is going to be 5. So just element by element addition, right? Exactly how you'd think addition would work for matrices. Let's do another example. 1, 0, 1, 0 plus 0, 0, 0, 0. Well, you're going to add 0 to each of these elements, which means you're going to get the first matrix back, right? This matrix is important. It's called the zero matrix, or a zero matrix of size 2 by 2. You will see this come up again and again. And if you perchance have seen any of my group videos, then this is our additive identity for the additive ring of matrices. Next major operation, scalar multiplication. What do we mean by scalar? Well, it means we're multiplying a matrix by something which is not a matrix, namely a number. And this is going to come in handy later, especially if you study linear algebra. But we can scale a matrix, if you will, and hence the name scalar. We're scaling all parts of it by the same amount, just simply by multiplying each entry by this number. So this would be equal to 5, 5, 0, 5, right? And in general, if you have a constant C in a matrix A such that it's given by this generic element, then the product CA is another matrix which is given by C A sub ij, right? Each element is multiplied by the number C, whatever that is. Scalar multiplication. Now at this point we can combine our two operations to make more fun, right? So suppose that this matrix is A and this matrix is B. Let's find A plus 2B. Well, that's just going to be 1, 0, 0, 4 is A plus 2 times B, right? And before we add these, we need to do the scalar multiplication on this one. So this is going to be equal to 1, 0, 0, 4 plus 0, 2, 0, negative 4. Now we add element by element. In each position we get 1, 2, 0, and 0. And that is A plus 2B. Very straightforward. Note that in that example, order of operations was determined by order of operations entry by entry. So because A plus 2B is going to be equal to A sub ij plus 2B sub ij, and this is going to be equal to A sub ij plus 2B sub ij, where we've now scaled each entry. This is equal to A sub ij plus 2B sub ij. Right, and multiplication comes before addition. We know how to do this. We know order of operations. Well, it's the same for matrices, just element by element, what happens first. So you multiply first and then add. So how do we multiply two matrices? Well, first of all, they have to have the same inner dimension. That means if we're taking A times B, then the second number, the number of columns in A, has to agree with the number of rows in B. This is just a feature of the way we multiply. You'll see why that's the case in a second. They're going to match up. So we're going to try and form this matrix A times B, or we're going to also call it C, represented by this generic element, little c sub ij. This is going to be equal to, in a certain sense, row I of matrix A times column J of matrix B. What do I mean by times? How do we multiply a row by a column? Well, we're going to take something which we call the dot product in math, but you don't have to know that term for it. All you have to know is how to compute it. So what we're going to do is the following. Suppose we have two matrices. Let's take a 3 by 2 matrix and multiply it by a 2 by 2 matrix. Can we do this? This is 3 by 2, this is 2 by 2. The second number here, number of columns, agrees with the number of rows here. We're good. Okay. Now how do we actually do it? And what's it going to give us, by the way? Well, we're going to end up with these other two numbers, m and p, as our dimensions of our second matrix. So in this case, that's going to mean a 3 by 2 matrix again. So what we're going to do is we're going to start with the first row and the first column. And we're going to multiply this row by this column. How do we do that? We match up entries one by one. There's a correspondence between the two, right? So we match up these two and we match up these two. And these pairs we're going to multiply together, and then we're going to add all those products up. So we're going to have 1 times 0 plus 0 times 0. 1 times 0 plus 0 times 0 is going to be just 0. Now for the second entry, right, which is going to be entry in row 1, column 2. So position 1, 2 means row 1 of this first matrix times column 2 of the second matrix. So now we're going to do the same thing. 1 times 1 plus 0 times 2. So you're moving over in this one while you're going down in this one. 1 times 1 plus 0 times 2. That's going to be 1. Now, for this one, what is the position here? It's going to be in row 2, and it's going to be in column 1. That means take row 2 of matrix A and multiply it by column 1 of matrix B. So we're going to have 1 times 0 plus 2 times 0. We're going to have 0 again. Now for the next one, once again, position 2, 2. We're going to take row 2, column 2. 1 times 1 plus 2 times 2. That's going to be equal to 5. Now we have row 3, column 1. Row 3, column 1. 2 times 0, negative 1 times 0. It's going to be 0. Last one, we have row 3, column 2. So row 3 times column 2. And this is 1 times 2 plus negative 1 times 2, which is just going to be a net 0. So this is our final product when we multiply them. Now let's write the general formula for this. Not because I want to confuse you, but rather because this is a deep underlying reality of matrices, and why they are so useful is that they multiply in this fascinating way. So what we do is for element sub I, j, right? Row I, column j of our product matrix is going to be equal to the sum from, we're going to introduce a dummy variable, the sum from k is equal to 1 to n, this is the inner dimension that has to agree between the two matrices, sum from 1 to n of a sub ik times b sub kj. Right, so what we're doing is we're keeping the row the same in matrix A, and we're keeping the column the same in matrix B, and notice how that agrees with the position in our product matrix. And we're going to be ranging over this, well, in this case, the columns for matrix A and the rows for matrix B. We're going to be ranging over this while multiplying together and then ultimately taking the sum. So this is going to be equal to a sub I1 B1j plus a sub I2 B2j plus etc. all the way up to a sub in b sub nj. And this sum is going to be our entry c sub ij in our product matrix, right? And again, I encourage you to study this and to learn to recognize this form, because learning to recognize matrix multiplication in this way will pay dividends, I promise. Let's do some examples. Let's multiply these two. Well, first, how are we going to do this? Well, suppose we could do this. Then we'd have, for the first entry, 2 times 4 plus 0 times 3 plus, wait, what is 1 going to multiply with? Now you see, this is the fundamental issue. We have to have a one-to-one correspondence between rows and columns, because otherwise we have some entry left out which doesn't multiply, and our product is not going to be well defined. So notice that this is a 2 by 2, and this is a 3 by 1, and 2 does not agree with 3, so we cannot multiply these two matrices together. How about these two? Well, we have a 2 by 2 matrix here and a 2 by 1. 2 by 2, 2 by 1. These two numbers agree. We're good. So let's do it. What is this going to be equal to? Well, we're going to have 3 times 5 plus negative 1 times 0. It's going to be 15. Then we're going to have, for the second row, we're going to have 1 times 5 plus 2 times 0, which is going to be just 5. So it's going to be another 2 by 1 matrix, 15 and 5. Let's try this. How about a 1 by 3 matrix times a 3 by 1 matrix? Well, the inner dimensions agree, so we can do it. And the outer dimensions, 1 and 1, tell us we're going to get a 1 by 1 matrix as a result. When we have this, we usually define it just to mean a scalar, just a number. So let's look at what we have here. We'll have 8 times 5 is 40, plus 9 times 0 is 0, plus 1 times 10 is 10, is equal to 50. So you see, you can take these a 1 by n matrix and multiply it by an n by 1 matrix and get a number. This is an important concept, and this is really what's going on inside of matrix multiplication. You have a row and a column, and together, if you multiply them as matrices, you get a number, and that number is the entry of this row and this column in your product matrix. Let's do another. How about this matrix times this matrix? Well, we'll have 1 times A plus 0 times D plus 0 times G. Well, that'll just be A. Now for this position, for second column, first row, or first row, second column, we'll have 1 times B plus 0 times E plus 0 times H. So we'll have B. Looks like we're going to have a similar story here in the third position, C plus 0 plus 0. What about for the second row here? Well, we move down a row, start over again on this first column, 0 times A plus 1 times D plus 0 times G. Well, that's just going to be D. Similarly, these two are going to be 0 and this is going to be 1. So E, 0, 0, 1. And the last row, it's going to be the same story. And you notice that these two matrices are equal. And for this reason, we call this matrix, this is a very special matrix. It's called the n by n, or in this case 3 by 3 for its dimensions, 3 by 3 identity matrix. Why the identity matrix? Because it gives you back whatever you multiply it by. It's like an identity. It's like the number 1. In fact, the parallels between this matrix and the number 1 in just normal algebra are pretty strong. And this will be true no matter which way you multiply it. Suppose you multiplied it on the right, you'll still get back this matrix. So this is the n by n identity matrix. It's always a square matrix with 1s on the diagonal, the main diagonal here, and 0s everywhere else. Now, a very interesting feature of matrix multiplication is that in general it is not commutative. What does that mean? That means that AB is not necessarily equal to BA. Normally with numbers, you have 3 times 4 is equal to 4 times 3, right? 3 rows of 4 objects is the same as 4 rows of 3 objects. You're still going to get 12. Well, with matrices, one of the beautiful little quirks of our definition of multiplication is that this no longer holds. And this is actually a good thing, although it may take you some time to see this. So let's do an example here. So 7 times 0, you see this matrix is the same as this one, and this one is the same as this one. We're just going to multiply it both ways and see what happens. Well, 0 plus 3 is going to be 3. 0 plus 0 is 0. 0 plus negative 3 is negative 3. 0 plus 0 is 0. Okay. Now, what about multiplying them the other way? 0 plus 0 is 0. 0 plus 0 is 0. 21 plus 0 is 21. And 3 plus 0 is 3. You see, these two matrices are not the same, right? So if AB were equal to BA, these would be the same, and they're not. So, counterexample. Be careful of that. Make sure you're multiplying matrices in the order you intend to. How do we define exponents with matrices? Suppose we have a squared, where a is a matrix. What does that mean? Well, we just define that to mean a times a, right? And a cubed, similarly, is just going to be equal to a times a times a. And matrix multiplication does have associativity, if you know what that means, which means that we can put the parentheses in like this, or we can put the parentheses in like this and multiply these two first before we multiply by the other one, and it doesn't matter. You will get the same answer. You can't generally flip things around like AB equals BA, because that's not true, right? The commutative property does not hold, but the associative property, A times B times C is equal to A times B times C. That is good. It still holds, and all is well in the universe. All right, let's take the square of this matrix. So we have 0, 0, 10, 0. So this is just equal to 0, 0, 10, 0 times 0, 0, 10, 0. All right, let's multiply that out. 0 plus 0 times 10 is 0. 0 plus 0. 0 plus 0. 0 plus 0 equals the zero matrix. This is interesting. So we have a matrix here with a non-zero entry which squares to the zero matrix. Let's try this again with another. We're going to take the cube of this matrix. Obviously this is not the zero matrix. We've got these three entries are non-zero. So this is just going to be 0, 1, 2, 0, 0, 3, 0, 0, 0 times 0, 1, 2, 0, 0, 3, 0, 0, 0 times, and let's do the first two together first. 0, 1, 2, 0, 0, 3, 0, 0, 0. Okay, so we'll multiply these two together first to get 0 times 0 plus 0 plus 0 is 0. It's our first entry. Second entry, 0 plus 0 plus 0. 0 plus 3 plus 0, so that's going to be 3. 0 plus 0 plus 0. 0 plus 0 plus 0. 0 plus 0 plus 0. And more zeros. Lovely. Okay. But notice this 3 in there. This is not the zero matrix, right? It does have a non-zero entry, and then we're going to multiply it by the original matrix one more time in order to get the cube. So this is going to be equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. All right, so the first row is all zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0. All zeros, and I'll save you the trouble. The last row is also going to be all zeros. This is none other than the zero matrix. Well, this is peculiar, isn't it? If we call this matrix A that we started with, not only last time did we have one which squared to the zero matrix, but now we have one where A squared is notably not the zero matrix. It's not, because it has this 3. But A cubed is the zero matrix. What exactly is going on here? Well, the bottom line is that matrices are not like real numbers, right? They don't have the same properties. Even though matrices are made up of numbers in a sense, right? They're arrays of numbers. Arrays of numbers do not necessarily have the same properties as the numbers themselves. Notably, for any real numbers x and y, any numbers on the number line, we would have x times y is equal to 0 implies either x is 0 or y is 0. Why? Because the real numbers have this property that there are no what's called zero divisors, and this is that property. There's no number that multiplies by another, no non-zero number which multiplies by another non-zero number to give you 0. It's part of what's called being a field. It's a field of numbers, and matrices do not form a field. Now that's just some math jargon that you shouldn't know at this point. So essentially what you just need to realize is that the structure of matrices is fundamentally different from that of numbers. They have similar properties, like the fact that you can add and multiply them. But once again, there's no commutative property. AB is not equal to BA in general. Sometimes it's true, but it usually isn't. Don't count on it. And there are zero divisors. So we need to treat matrices on their own terms as separate mathematical entities from what we've dealt with up to this point in math. Notably, the matrices which we were just looking at have another special property, so that if you have some matrix A and you raise it to some finite power and you eventually get the zero matrix, you multiply by itself enough times and you get back the zero matrix, then that matrix A is called nilpotent. Nilpotent matrix. And nilpotent matrices play a very fundamental role in what's going to turn out to be the main theorem of our matrices series, the Cayley-Hamilton theorem. So keep this in the back of your head. There are matrices which square, cube, etc. to 0, or, hint, 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 satisfy a polynomial as a root. Alright, let's put together everything we've seen so far and really explore what I'm now in a position to call the algebra of matrices. So we have a matrix A, which is 2 by 3, and a matrix B, which is 2 by 2. Let's take B times A in that order and subtract 6A. B times A, is that going to be well defined? Well, 2 by 2, 3 by 2, yes it is going, or sorry, 2 by 3. It is going to be well defined, and it should give us back something which is 2 by 3. We're going to have 5, 0, 4, negative 1 times 1, 0, 0, 0, 1, 0, minus 6 times A, which is 1, 0, 0, 0, 1, 0. Okay. Once again, order of operations, we need to do our multiplication first, and that means both kind. Matrix multiplication and scalar multiplication we need to do before we can do matrix addition. So this product is going to be, let's see, 5 plus 0 is 5, 0 plus 0 is 0, 0 plus 0 is 0, 4 plus 0 is 4, 0 minus 1 is minus 1, and 0 plus 0 is 0. And then this matrix, we're going to multiply everything in it by negative 6 to get negative 6, 0, 0, 0, negative 6, 0. Alright, now for our final operation, we're going to add element-wise. So 5 minus 6 is negative 1. Zeros add to 0. 4 plus 0 is 4. Here we're going to have negative 7. And 0 in the last position. So here is our final answer. This is BA minus 6A. And if you can do that, then we're well on our way to being comfortable with matrix algebra.